foreshadowing on the warm-up. Today we want to discuss this topic, the last of the unit, derivatives of inverse functions. And actually, we could have done this earlier too. We're never sure exactly where to put these lessons. I think your book has actually 3.8 is the section where they talk about derivatives of inverses. It's also the section I think where you're doing the inverse sine function, for example. So all these ideas are connected in a nice way. You can check out Ian's work on the board now. He's written it up here. And see why. In fact, yeah, we get 1 over cosine y. I like that. For reason, I want to keep that. I might refer to that, in fact, in our lesson today. Maybe there's a deeper truth to get at there. Okay. Ian's done us a good favor there. All right, so we would like to think about this as being kind of the central question of today. Now, let me apologize here. You guys are much further over on the left side than you normally are. Can you see okay from there, you four? There are two solutions I have in mind right now. You could all move there, or we can move you back. We could all cooperate to move you where you should be.
We can all cooperate.
Or we could do both. Why don't you guys especially move? You think you'll hold time. But you guys do whatever you want for the benefit of your education. Okay? I feel bad. And there might be a bit of glare. Do I need to close this? I just want to make sure. So I have a series of questions for you about Algebra 1 style here. Algebra 1 questions for you. So I'll put a couple up here. So I think it should be fairly, you can just even shout out the answer to the first one. This is just a line. So what's the slope at 6, 3? Good. By the way, except that's a little bit of a troll. I didn't even. If you plug in 6, you get 1. Just kidding. There's no slope there. Okay. No, it is 3, isn't it? Yeah. Okay, I was right. All right. I thought I was crazy there for a second. All right. Oops. Okay. 6, 3. So it is 2/3. What's the corresponding point on F inverse? 3, 6. What's the slope of F inverse at that point? 3 halves. I don't know if you've ever actually been asked that before. It's certainly a question you could ask an algebra 1 student. I just think we don't usually. I don't know. Right? And then what? Do you have any conjecture to make about what just happened? Do you think this is? Do you think how widely applicable might your conjecture be? I think you might make the conjecture that F and F inverse. I mean, it's certainly true for any given 2 lines. That what's the relationship between the line and its inverse line? It's in terms of the slope. In terms of the slope, I guess I should make you say. The slope of the original was 2/3. The slope of the inverse is 3 halves. And what relationship do those have? Of course, yeah. Yeah, so maybe we, I don't know how big a conjecture we want to make, but at the very least, I think I'm fairly convinced that that's true of every line and its inverse, right? And even though it's pretty simple to say, could you prove that? Maybe you could prove that. Could you use an algebraic argument? Maybe all you need is a geometric argument. I don't know. Right? So no calculus really yet in a major way. But now let's talk about a curve and ask if we can ask some of this. I'm going to have the exact same 4 questions I'm going to ask you. So I'm looking at just the positive part of the graph of x squared, and I already have the inverse graph there. And so the first question is, what's the slope at 2, 4? This is a non-trivial question this time. Last time it was just of course it's 2/3. Just look at the equation. It's always 2/3. Yeah, but it's not too hard here. It's just 4. Good job. I'll put that up there. What's the corresponding point on F inverse? That's not the hard part of this yet. That's, of course, 4, 2. And now the question is, what's the slope there? Well, we could actually compute it, right? So find F inverse. Let's actually do that. Here we go. And I insist that, Ian, you do it your way, maybe. You should do it your way, just for fun. Right? Are you with me? Okay, we'll all do it the way that we're thinking of. We're all thinking f inverse of x is root x, yeah? So then continue, right? Just take the derivative and evaluate it at something. At what? For this particular case, what value will you plug in for x? Yeah, not 2, but 4, right? So go ahead and find the derivative if you like. And that'll be great. Plug in 4 then. So now I have a little bit of an issue here, mathematically, like notation wise. I just call this f inverse. How do you want to note the derivative? F inverse prime? F inverse prime? I'm going to get a little confused by that. So now I'm kind of seeing why on the warm-up I used, like, if this is f, let's use Leibniz notation. That's like one more reason maybe that we sometimes like Leibniz notation. So because this is a little clearer, isn't it? I think if you have an inverse and a prime, like we might get a little messed up in Leibniz. So we'll maybe write it that way. I don't know. So yeah, you get 1/2 x to the negative 1/2, and you plug in 4. Right? All right, we'll go back here and put it in here, but and what do you get? So that's 1 over, this is 1 over the square root of x, isn't that? We could even write that way if you like. 1 over 2 times the square root of 4. So what do we get? 1/4. And let's see if that's what the survey said. Yeah, m equals 1/4 for the second line. So again, let me ask you to make another conjecture, to ask what you wonder. The conjecture you made on the last slide, does it seem to work here too? I remember Josh saying just 2 minutes ago that his conjecture was that they're reciprocals. They have reciprocal slopes. That seems to be the case still here, doesn't it? So, how did you do, Ian? Did you do it your way? And did it work out? Can you do it on the board again? You're just so good at this here. Let's keep sending it over there. Because I'm interested, maybe there's like some observations we can make kind of at a higher level here. The other thing this makes me think of too is no one ever took me up on proving the power rule, except for I think Kira proved the power rule for the result here, right? For n, for positive integer n, I think is all she proved it for. Using the binomial theorem or something like that, wherever you are, Kira. But no one ever took me up on it for the derivative of x to the 1 over n, right? I mean, that should be, you know that you can do like the derivative of x to the 1/2 is 1/2 times x to the negative 1/2, right? Just because someone told you so. But no one has proved that yet, actually. Does the power rule just always work? Well, this suggests maybe in general a way of doing this, right? Maybe, right? Like maybe if you know implicit differentiation and you know the normal power rule, then what relationship do these functions have? Well, they're just inverses of each other. So maybe you can, maybe that gives a way in on that proof if you haven't thought about it yet. So I'd be really interested to know if we can just get at every root function now, proving that in general. But do you like Ian's way of doing it too? Using implicit differentiation? It's kind of a nice way to do it too. Great. And in general, can we make a claim about all functions now? I think let's try to do that. I'm going to use the same picture here, but I'm going to actually use, let's pretend we don't know what these functions are. And see, can you actually formulate what we just are now claiming in a really precise way? Let's call the point that we started with not 2, 4, but let's just call it a, f of a. How about? Let's be as general as we possibly can. Then the slope there, let's represent as being df dx evaluated at a. I know the notation's a little heavy, but do you understand, I think, what that means? So that's the slope, certainly, of the original line. So what's the point on the new function, the inverse? In terms of our notation here, it's f of a, a. There it is. And what do you claim the slope is at that point? It's 1 over what? I mean, it's not nice to say out loud maybe, but it's 1 over that thing, right? Whatever that is, which is absolutely right. So let's put it in a box. It's just a little hard to digest. Like, it really, this is one of those ideas that's like super clear until I tell you the formula in a box. Like, not all, sometimes it's the opposite, right? But in this particular case, it's like, I almost hesitate to give you the box because it so muddies the water so much. Like, you understood it really, really well a second ago. And now suddenly you're like, wait, what? So it's such a simple idea, and yet here comes the notation. It's just hard to say, isn't it, out loud? Well, here's how you might say it out loud, right? What does it say exactly? It says the derivative of the inverse, evaluated at f of a, like for our function it was 4, or whatever, is equal to the reciprocal of the derivative evaluated at a. Is it coming back into view again? It kind of comes in and out of it for a second. The idea is actually pretty simple though. This idea of the reciprocal slope. And that's like the whole point of what we're doing today. I just have I have 2 examples to show you, but we just wanted you to stop and realize this is true, right? And then now continue on your way, math sojourners. So is the notation clear enough for you? I'll leave that up there for just a second. Longer, yeah.
Is there a proof to this?
Well, your proof would actually entail just maybe making claims about the lines, really, right? A proof, well, you know from your previous courses, the relationship, the geometric relationship between f and f inverse, right? So one way in maybe would be to think about the fact that this is a reflection over the line y equals x, and that you have like a rigid motion that maps the x and y axis to each other, right? So all angles are preserved, all shapes, all distances are preserved. I might, before you prove like this higher level calculus idea, I might just ask you to go back and prove for, just in general, using geometry and algebra 1 style stuff. How do we prove that if we have like a line, say, going through the origin, and by the way, it doesn't matter if your line goes through somewhere else, let's just change our coordinate system to be at the origin. Let's say the slope of this line is a over b. Well, I need a different color. What would the slope be of the reflection of this over the line y equals x? Well, I think you'd get this picture. Actually, you don't even have to talk about reflections. Just by the definition of inverses, we have b, I guess I used b comma a, whatever, doesn't matter. We have a comma b, don't we? So what's the slope of that line? Is it clear, just like from very, very, very first principles, that the slopes are reciprocal? So that would be like maybe that needs a little more rigor, but I think that's like good enough for proving that 2 lines have that are inverses. That is, if AB is on one line that goes through the origin, and BA is on the other line, then they must have reciprocal slopes. And then this is not really, there's not much more to say. This is calculus in blue, but in red, it's still 2 lines, right? Like the calculus, the curves are in blue, but the lines are what we're asking about. What is the relationship between the slopes of the 2 tangent lines? Well, that's still this. That's still lines. Can we, maybe there needs to be a little more work to do. Can we prove that those 2 lines are inverses of each other? That might be one little gap to fill in. I don't know. Sorry, is that good enough? I don't know. Did I see it on here? You like the notation though? I put it on this slide too, just so in case you forgot it. Here's kind of an AP style way of asking this, and I'll give you then another kind of more traditional problem in a second as well. So go ahead and give this a try with your table, see what your neighbors get. 90% of this problem is you just understanding the notation, understanding what's given. Once you realize that, answering it will take you like 2 seconds. It's just like, wait, what? Whoa. Was I right that like 90% of the heavy lifting was you just like reading the problem? What did that say? And then you're, oh, of course, it's, well, I don't want to spoil it for anyone, but why don't you tell your neighbor what you got? Hopefully it's clear. I don't know. I left all this space so there's nothing to do except to write down the answer. None. I don't have anything to say about this. Except to just write down the answer, really. All right, so all together now. What do you say the answer is? Yeah, I mean, there's not much more to say than 1/6. Like, there's no work to write down or anything like that. It's just to be clear. Actually, maybe it's more work on the problem writer to make sure that all these things happen. The 0.35 is on the original curve. On the inverse, we have 5, 3. So does it even make sense to be asking this question at the end here? Oops, sorry. Yeah, absolutely. Does it make sense to be asking what is the derivative of x equals 5 on the inverse? Yeah, I think I get it now. This is that picture we were doing. And were we told the information we like on the original function? We know the slope is 6 at that point, so it'll be 1/6 on the, like that. I don't know what supporting work to show, except to be like, I know this is true, and I'll just fill in the blanks, right? But you know, AP likes to give you like context list problems that don't actually have functions. So this is a very kind of, they like that kind of thing. Here's a more traditional problem. I actually gave you the function, and I'm asking for the, don't just find the slope, go all the way and please give me the equation of the tangent line to this graph of G inverse at that point. Okay, so give that a try with the table. That might take a moment longer, I think. I have a follow-up question too, and that's this. Maybe all this isn't worth it. Why not just find the inverse? Could you do that? And I don't know. Would that be, what do you think of that question? I don't know. Okay, I mean, this is calculus class, so even if I have no idea what I'm doing, I might take the derivative of this thing. 4x is all I need, I guess. 4x. Okay. And in particular, the slope on the original curve at 1 is, what'd you find? 4. So then the slope of g inverse at 5, negative 5, it must be 1 over that thing. So I think I saw that as I walked around. Is that the slope you got? Okay. And then I think we're done. We have this point, we have the slope, just write down the equations. What is it? Did you get y equals 1 plus 1/4 times x plus 5? I think I saw people with that answer. So, I don't mean to give away the answer, but is that what you guys were finding?
Yeah.
All right. Hopefully that makes sense to you guys. Don't get lost. Go back to the pictures we were looking at today. Don't get lost in like the notation or the. Think about what the picture looks like. Okay. Well, I've got the slope on the original. What's the slope on the inverse going to look like? Make sure you're not plugging in negative 5. You know, make sure you're getting it right. Again, harder to like talk about than just to see. Yeah.
So on the unit test, when you get a question like this, are you gonna have to maintain like that kind of like notation, or is it alright if you just
Not necessarily. You should be okay with me asking a question in that way, though, like, right, and understanding how to interpret it. What about the last question? I mean, that was kind of notation heavy. Are you okay with it being asked that way? Yeah. There's not necessarily too many requirements for the work shown here necessarily, but as long as you understand how to get that answer. Before I show you the homework, I'd like you to try one more thing here. I'd like you to go back and do the warm-up one more time using this new method and see if you don't get the same answer. I mean, in some ways, you already did if you're Ian, maybe, but you kind of already did that, didn't you? So. Sorry, it's 3 again. I copied and pasted. I don't think we need to go over this or anything like that. I'd like you to do it, and if you got it, then you got it. Now, there was a question that I put up here a second ago too that no one answered yet, and that's why not just find the inverse on that last problem, for example, or on this one? Give a reason or some reasons why this might still be useful to talk about. Right? It seems like you were happy before, like why do we need this? I don't know. Anyone have a good reason? Did you get 2 again, by the way? Oh, I'm gonna go off this slide here. Okay, so I'm sure you did. So the question I asked on the last slide a second ago was this here up at the corner. I said, why not just find the inverse?
That's what I did.
Did you?
Yeah.
And you still got the same answer. Took you maybe a little longer, but maybe not. I don't know. Yeah, I mean, it did work though.
It did work, yeah.
So one reason might be like it's sometimes infeasible or annoying or something. Would be a good reason.
I just forgot to
Or you forgot or something. The other reason is, as you look at the problems I'm going to ask you to do for homework tonight, which are here, and actually this is it. You can either go, these are available on that Visual Calculus website, or you can write them. I mean, you actually still have 7 minutes to get started. You could actually start working on them right now. Or you can take a picture if you like. Okay. Looking at this, I have another reason though too, that finding the inverse might be maybe even infeasible, right? Like what if I gave you one like this first one, well, Mr. Chase, I hate this new technique. I would just like to just find the inverse of this and actually compute the, wait, hold up. What if it's not, what if it has an inverse that isn't a function, right? Or what if it's impossible to solve for? You can still use this technique, right? Can't we? So notice that, in fact, almost every single one of these, like you finding the inverse first, taking the derivative of that, that's just not a method we can use on any of these, really. So just keep that in mind. All of these points are on the inverse. Okay. By the way, you might need to take another picture so you didn't catch that. Yeah. Okay, so that is the homework right there. It's on that website. There isn't a handout. I don't know why I said that. Just the website problems. These problems are the homework. That's it. Okay. You can start working on them now if you like. And the solution button there, you can check online, right? Just like you did before. The worked out solution is on the Visual Calculus website that you used before. The implicit differentiation.